Okay, welcome everyone. So welcome to the seminar. So it's my pleasure to introduce Zenna Tavares. I've been following Zenna's work on probabilistic programming for at least 5 years. So he's currently a postdoctoral researcher at MIT, working with Armando Solar-Lezama. He's also affiliated with the cognitive science group there, led by Joshua Tenenbaum. And what I like about Zenna is that he's simultaneously a deep thinker about kind of core problems in probabilistic programming, but also a hacker who just builds Julia libraries and thinks that's a lot of fun as well. And so that's something I can appreciate. And so today he's going to talk about common sense reasoning through causal probabilistic programming. Zenna, the floor is yours.
Thanks, Guy. Let me share my screen. It says host disabled screen sharing. Am I not on the right link?
No, you should be a panelist. So let's see if I can change that. So I think maybe now it will work.
Cool. Okay. Can you see my screen? Okay.
Yep.
Cool. So yeah, thanks for the introduction. My name is Zenna Tavares. I'm a postdoc at MIT. Today I'm going to talk about mostly my PhD work and over some stuff over the past few months during my postdoc, also in the same lab at MIT. This work is done with many people who I'll acknowledge at the end, but largely with my advisor, Armando Solar-Lezama. So the title of my talk is Common Sense Reasoning through Causal Probabilistic Programming, and I'll get into what that means. So when I see an image like this, I immediately have many inferences. So I can predict possible futures, what will happen. I can also infer kind of plausible histories of how we got to this point, in particular, that somebody took a Jenga brick to cause this to fall down. I can ask causal questions, what is it that caused this to happen? Or counterfactual questions. Had we done something differently, would a different scenario have arrived or occurred? At lower level than these higher kind of questions, I can also figure out what is the underlying scene here. So this is a two-dimensional image because you're seeing it through your monitor, but there's an underlying three-dimensional scene which, in some sense, causes the two-dimensional image that you see. And so when I say common sense reasoning, I'm really talking about this inclusive or expansive notion of how do we do inference at these multiple levels of both probabilistic reasoning and causal reasoning using different kinds of models about the world. So the idea or the paradigm that I'm working in mostly is this idea of having a simulation model in your mind, right? And so the idea again is that you have some kind of simulation, physical simulation, almost like a video game engine inside your mind, and you can use that simulation engine to ask questions. And so when we pair these two things, one, the ability to simulate, and two, the ability to use that for inference to ask different kinds of questions, many different kind of paradigms of reasoning become possible. This idea of a simulation in the mind is not my idea. There's a lot of existing work in cognitive science behind this idea. So taking this Jenga example that I showed at the start, there's some work by Peter Battaglia, formerly at MIT, now at DeepMind. And he basically shows that you can construct a good model of human experimental data using this kind of simulation model. In particular, they ask people to predict how a tower of blocks would fall over under different scenarios. And they have a stochastic simulation which predicts well the experimental results. Now, the stuff by a colleague of mine, Julian Harry-Ettinger, and here the simulation in the mind is simulation of other agents. So you're thinking about how other people are thinking about how they're thinking. And again, you can get good models of experimental data. On the right, we have these, the task here is to predict the object underneath the cloth. And they show that having a kind of a physical simulation of cloth allows for a good experimental, a model which matches well the experimental data that humans give. And again, the idea or the implication is that in order to answer this question, you have a simulation, a cloth simulation in your mind, and it allows you to decloth the item to answer these queries. And so my work is somewhat at the intersection of probabilistic programming, reasoning, cause and inference, very much inspired by a lot of the stuff in cognitive science. And the talk I'm going to give today is divided into these 4 parts. First, I'm going to talk about generative models. Then I'm going to talk about counterfactuals in those generative models. Following this, I'm going to talk about something I call learning algebraic structures, which is more on the machine learning side. And finally, I'll talk about different open problems and things that I've been working on more recently. So what is a generative model? This is a term which, as far as I could tell, goes back into the 1950s, originally with Noam Chomsky, where he describes a generative approach to language in the sense that you can generate sentences from the language, and in some sense, that describes the language itself. In the 1980s, this term generative model was somewhat adopted or co-opted more by the probabilistic people or probabilistic reasoning people. And it was used in the context of a graphical model for the most part. So we describe a model which we can generate values from this distribution. And again, more recently, the term's been, again, largely co-opted more by the machine learning community, where generative model in this sense means some kind of neural network where you can generate images like this image on the right-hand side, which is not a real person. So GANs and VAs and things like that. But the underlying idea of a generative model is can be formalized in many different ways. The way that I like to think about it is as an algorithm which transforms some uncertain input into data. So I'm sure everyone knows what an algorithm is, but let's dig into these different parts. So the data is just what we described, images, text, and so on. And the uncertain input is what I'll describe next. So the input to a generative model, at least in the way that I'll formalize it, is just comes from these primitive distributions. So let's say a normal distribution or a Bernoulli distribution or a uniform distribution. And given these primitive distributions, a probabilistic generative model is simply a transformation of these distributions. So in this case, I'm putting as input a normal distribution, then I apply some transformation on it, and in this case, the square function and then the log function, and the result is this transformed distribution. And it turns out that this simple paradigm of starting with some simple primitive distributions and applying transformations to it, we can actually construct very rich and complex output models and output distributions. And so one way to think about what a generative model is to think about what it is not. And so, and sometimes people talk in terms of implicit models and explicit models. And the distinction is that in a generative model, kind of the probability that the model takes any particular value is not explicit, it's implicit in the model, right? So we often cannot directly compute like how likely is the value of X. In contrast, in an explicit model, we have a function which takes as input some data and gives me a density or gives me a probability. And so I'm working mostly on the implicit generative models. And this is important because these arise when you start trying to build stochastic simulations. We're often more in this regime where we can simulate the model, but we can't actually compute any particular probability or any particular density. And that somewhat biases the kinds of methods that we can use. So let me give you a simple example of what generative models are used for, which is inference. And so the high level point is that given some model, we can ask questions and we can ask any question in some sense. So here's a simple example. Suppose that Alice has a coin and that coin has some weight. And so the weight of the coin, if the weight is close to 1, that means that the coin's going to come up heads more often. So we can model this coin weight with a prior distribution, a beta distribution. And now suppose that Alice flips the coin and we observe some data. So if the coin lands heads, the question is, what should we believe about theta? And this is the Bayesian inference problem. And so we can solve this using Bayes' rule. So we can do this transformation, and the first step is to use Bayes' rule to derive the posterior distribution given what we know, which is the likelihood function and the prior function. And I'm sure most people are familiar with this. And then the step 2 is that given that we've got this posterior function, we still have to use some kind of inference method, for example, MCMC, to draw samples from this posterior. because the posterior by itself is often just something that we can evaluate at particular points, but what we want are samples from the distribution. That's the end goal. But often one of the things that I found is that people conflate Bayes' rule with Bayesian inference, and these are not the same thing. Bayes' rule is a mechanism to do Bayesian inference, but Bayesian inference by itself is a kind of a methodology to update our model with new information. So let's build a generative model of this Alice coin example. So first we need to define a distribution for theta. And the way that I'll do that is start with this primitive uniform distribution, and then I can transform that into a beta distribution. And if that's not obvious that we can do that, you can just take my word for it that there is a transformation that turns a standard uniform from 0 to 1 into this beta distribution, which is symmetric around 0.5. And then we do the same thing for our Bernoulli distribution. And again, a Bernoulli distribution is just is either true or false, heads or tails, 0 or 1. And again, we can construct a Bernoulli distribution as a transformation from a uniform distribution. The key point here is that the parameter theta goes from the beta into the Bernoulli. This is what creates a dependence in the model. So the key point is that I've now observed some data. So I'm saying that the output of A is H, and now everything becomes updated. The most obvious thing is that the coin goes from being a fair coin to having all of its mass on heads. But more kind of importantly, our belief about theta has now changed. Like before we believed that theta was symmetric around 0.5, and now it's slightly shifted towards 1, which you should expect. Like we've observed that this thing is heads, and now our belief changes about theta. But all of the other distributions have changed, and here's the reason why. So if we think about what our model is really saying, if we think about this primitive input to our model, like I said, we have this uniform 1, uniform 2, and for any particular point in the space, for any particular combination of values, everything else is determined. In particular, the output of the coin flip is determined. Now, when we condition, we make a statement that A is equal to heads. What this really means fundamentally is that we are going to eliminate everything which is inconsistent with that data. And so we go from this regime on the left-hand side where everything's possible to this regime on the right-hand side where some things are now impossible and removed from our distribution. So conditioning is really the operation of adding information to our model, which is restricting our model to be consistent with some data. So everything I've said so far was in the context of probabilistic generative models. What I work in particular is using programming languages to describe these generative models. And programming languages, in some sense, bring a fundamental advance in the sense that they describe universal models of computation. Universal in the sense that you can compute any function and therefore you can compute any distribution. But more practically, it means that we can use all the things that we like in our programming languages like control flow, recursion, data structures, composite functions in order to describe our probabilistic models. And what we need from our probabilistic programming languages is to support universal inference in these models, or to be able to allow us to ask questions and derive answers. So here's a more complex example than this coin example. And this is sometimes called inverse rendering or inverse graphics. So suppose you see this image, well, we don't need to suppose, you do see this image of these balls, and what you want to infer is the three-dimensional structure behind this scene. And immediately, your mind is somewhat doing this automatically already, I imagine, or I hope. And so the task is to build a system that can somehow take as input these two-dimensional images and as output produce some latent representation of this world. And that could be the number of balls, and for each balls, different parameters, the origin, the radius, surface color, emission color, and so on. So how should we do this? So the first thing we have to do is to build a generative model of this scene. And so we start with the kind of our primitive distributions, which I've got as this omega on the left-hand side. Then we apply some transformation S, and we get this distribution over three-dimensional scenes. And then if we render these scenes with some rendering function, which simulates light, the kind of thing you see in a video game engine, we now get a distribution over two-dimensional images. And so for any particular point in the input space, we get out a different 3D scene, and we get out a different two-dimensional image. And what we want to do is to condition the output and to say that we know what the output is. We've observed something in the real world, And what we want is the posterior distribution over three-dimensional scenes given this observation. So if we just focus a little bit on the first part, this model, this generative model over three-dimensional scenes, one of the things that we can do in a probabilistic programming language, which is not possible or at least difficult to do in other formalisms, is to model these kind of open world models. And what that means is that the existence of objects themselves is uncertain. So here's how we could do it. We could say that n is the number of objects, and then we're going to sample n from some distribution, for example, a Poisson distribution. And then we're going to make a collection of n spheres, and each sphere has a number of different properties, a radius, an origin, and color, and so on. And each one of these things itself is a random variable. So we have an unknown number of objects, and each one of these objects has parameters for each of its properties, which is random. And we can run the forward model and draw samples from scenes and render those scenes, which is what I'm showing you here. And so for different possible inputs, we get different numbers of objects, different properties, colors, and so on. So these are just samples from our priors, from the prior distribution rendered, and that's what I'm showing you on the screen. But there's an issue, there's a problem. And the problem is that in the real world, at least the real world for the purposes of this presentation, solid objects do not intersect. But in the prior that I just described to you, they do intersect. We've got these objects going into each other, as you can see right here. And so we have this high level knowledge that in the real world, there's something that we think is true, but in our model, it's not true, right? And so the question is, what should we do in this scenario? So one thing we could do is go back and rewrite a new prior, right? We could try to construct a new prior such that by construction, objects do not intersect. But it'd be nice if we could not do that and somehow just tell our system that objects don't intersect, and the system would adhere to that constraint. And if you think about all the kinds of declarative knowledge that you have about different things, just things that you know are true, we want our systems to be able to take these statements which are true and incorporate them into the system. And so conceptually, we don't actually need any new machinery to do this. We should just be able to condition on it. So the idea is to incorporate, in order to incorporate this fact that objects do not intersect into a model, first we're going to write down a program, a predicate, that checks if this fact is true, and then we just want to condition on this fact being true. Okay, so we have the same model as before. We've got n and theta and so on. But now we have this program or this predicate p, which is this function of theta, this function no intersect. And what we want to do is to find the conditional distribution over theta, given that p is true. So we can try and go back to our Bayesian inference world and just do what we did before, which is to use Bayes' rule to derive a definition of the posterior. But now our likelihood function is this thing which is just going to be 0 or 1. So 0 if there are intersections. Sorry, it's going to be 1 if there are no intersections, and 0 if there are intersections. And then we can try and use MCMC sampling to sample from this kind of new posterior, or at least this new conditional distribution. And so the problem is that our likelihood function is going to be 0 almost everywhere. In other words, it's going to be hard, almost impossible actually, to find any values which are consistent, right? Because in the prior that I described, most of the things do not adhere to this constraint. And so most MCMC methods will not work. They just won't be able to find you any points which satisfy your data. And so we need to try a different approach to this problem. And so an idea we had, which is in a paper from last year, is based on a few ideas. The first idea is to give some kind of partial credit. And in other words, to compute the degree to which these conditions are met. So I've got 3 examples here. And in the leftmost example, the objects are not intersecting and everything's fine. And in the middle example, we've got a small amount of intersection. And on the right-hand side, we've got a full kind of overlap. And so the issue is that from the point of the predicate, whether our constraints are satisfied or not satisfied, there's no distinction between this example on the right-hand side and this example on the middle. Whereas intuitively, we think that this example on the middle is almost correct if we just have to make a small change to rectify it. Whereas this example on the right is very much incorrect. And so how can we get some notion of partial credit to be able to help our system? So the second key idea is that these predicates are not black boxes. And so we can actually look inside the internal structure. So this function no intersect, it's pretty straightforward. We actually just look at every combination of different balls pairwise, and we check whether the distance between the balls is greater than the sum of their radiuses, right? And if it is, then there are no intersections. And so the third insight is that all our predicates, any predicate that you can write in the language, is actually composed of a small number of primitives: conjunction, disjunction, equalities, and inequalities. And actually you can make an arbitrarily complex predicate, and it's going to boil down to a very small number of primitives. And so this all leads to an approach which is to say, let's take our predicate and let's take these Boolean functions, or functions which produce Booleans, and replace them with a soft counterpart. And so what do I mean by soft? So let's take a greater than b, for example. So the soft counterpart of a greater than b measures the degree to which I would have to increase a until it's greater than b, right? So a normal hard predicate is either true or false, but a soft predicate is a value which is between 0 and 1. So when it's 1, it means that the thing is true. So a really is greater than b. But when it's less than 1, it means that a is not quite, a is some amount less than b. And for each one of these primitives, greater than, less than, equality, and logical operators, we have the soft counterpart, which again is a relaxed notion of how close we are to satisfying this constraint. One additional thing is that this relaxation has a kind of parameter, a temperature parameter, which determines the degree to which we are relaxing the predicate. And I'll show you what that means in the next slide. So here I have a equals b, a is less than b, and a is greater than b. And so, and we're going from top to bottom in terms of increase in temperature. So at the lowest temperature, the system is very much like the hard constraint. So a equals b, or a soft equals b, is very much like the constraint, just hard a equals b. And similarly for greater than or less than. But as we increase the temperature, we can see we get more and more relaxed. So more and more things become closer to our constraint being satisfied. And at the limit of infinite temperature, then everything is satisfied. There's no distinction. These soft primitives compose. So if I have a function like b is greater than a, or b is greater than 0.7, we have this composition, and we get this, this somewhat more complex shape, but it's a relaxation of the true hard shape. We can also take the negation in another form of composition, and we get kind of the complement of this. There are some technical details which are in the paper where we could discuss later, but the high level point is that we have a complete Boolean algebra in which we can describe all possible predicates. And so the high level idea then is to take our program and take every kind of function, primitive function in that composition, and then replace it with its replace it with its softened counterpart. So we take equality and we replace that with soft equality and so on. And so now we have a composite function, which is itself a soft function. And so going back to our predicate no intersection, we've taken the original hard predicate and we've replaced the greater than with soft greater than, and the conjunction with a soft conjunction. And then we go back to our Bayesian inference formulation, and rather than conditioning on P, we're conditioning on soft P, right? And soft P is constructed by taking the intersection or the no intersection predicate, applying this transformation, which is really a program transformation, and getting out a soft likelihood and correspondingly a soft posterior. And then we can use this soft posterior as a kind of quasi likelihood function to do MCMC sampling. And so what this means is that we can take our generative model over 3-dimensional scenes, which before would create these these samples where we had these balls intersecting, and after we've applied this transformation, we get out this new prior in which no balls are intersecting, right? And so in some sense, this is an unusual kind of Bayesian inference because we are conditioning the prior in some sense, but it's still within the realm of kind of probabilistic inference. And what it allows us to do is, by using this notion of partial credit, we can condition on things which are very hard to do otherwise. now we can go back to our original problem of inverse rendering, and we can, and so what I'm showing you here is two images. On the left-hand side, we have the observed image, and on the right-hand side, we have an inferred image. And the high-level point here is that these two images are the same. And so and the way that we do this is very much the same as what I just showed you with the soft predicates. We condition the output of our model, the output of the rendering of these three-dimensional scenes on some observed image, on some observed image using a soft notion of equality. And that allows us to do inference by finding the three-dimensional scenes which are consistent with our observed data. And so the point here is that these two images are the same, which is kind of indicative of the fact that our system has been able to solve this constraint, that it's found three-dimensional scenes varying over the number of objects, their colors and other parameters, such that it's consistent with our observed data. And because we have a complete algebra, we can combine these two different facts. So what I'm showing you on the left, well, in both of these images, the yellow means that there are no intersections and the red means that there are intersections. And so if we don't add this no intersection constraint, we get these red regions. So we're doing both inverse graphics here. You know, we've got our rendering and we're observing the output image. But when we also add the constraint that there should be no intersections, we both find a consistent image, but also an image which has no intersections in it. And so the point of adding this constraint is that when we have knowledge about the world, which is true, when we add it to our models, we get better inferences. This is just a kind of a fact of Bayesian inference. And so the high level picture of this project is to be able to provide a mechanism by which we can encode high level declarative knowledge into our generative models, and also to do kind of normal inference at the same time. So one kind of thing this has shown is that inference is hard, and inference is hard for two reasons. The conventional reason, which many of you are familiar with, is that you have this integral in kind of Bayes' theorem, which you have to somehow account for. But there's another reason which is hard, which I think is less explored, which is that if you really give yourself the full power of a probabilistic programming language to describe both your models and your queries, then you have this needle in a haystack problem, where I have to find values which are consistent with my data. And a lot of the kind of the conventional work you'll see on Bayesian inference doesn't treat this problem, because they just assume that everything is consistent with their data. But there's a whole host, I would say maybe even the majority of problems, especially if you're in the simulation in the mind regime, where most things are inconsistent. And so we need a new kind of paradigm of inference methods, which allow us to solve for this consistency issue. And this is just one way that we've tried to solve this.
Then I can interrupt with a question about the previous slide. So I would maybe, no, the next one, about the needle in the haystack. So I was thinking there's actually maybe a third problem, which is once I found the needle in the haystack, how do I find another needle in the haystack? Because moving from one needle to the other with MCMC, I'm going to have to go and intersect a few of these objects. And so I wonder if you can say something about that.
Yeah, so this actually is tied in with this temperature parameter, right? So I said there's this parameter, which I'm showing you here, which kind of varies the degree of the relaxation, right? And so if you add if you're at a really high temperature, you can explore very large parts of the space, but you'll have a lot of error. And so what we actually do is we do MCMC at multiple different temperatures, and we combine the results in a method called parallel tempering or replica exchange. And so the reason this is called predicate exchange, this high level method, is because one, we have the predicate relaxation, and two, we use this approach called replica exchange. And conceptually, we've got multiple different MCMC chains running in parallel. And at the high temperature, we're exploring large parts of the space. And at the lower temperature, we are kind of sampling accurately. And it turns out that you can combine these different chains in a coherent way such that you get the best of both worlds, allowing you to explore, through these non-local points, as you mentioned. That's one way to. There's potentially many other different approaches to solving the same issue, but it is a hard problem, yeah. Okay. So I'm going to talk next about counterfactual generative models, which is kind of embedding causal reasoning into generative models. And so the motivation are images like this. And so when you see this image, or when I see this image, I immediately think, this driver is lucky. And I can explain my reasoning in many different ways, but a lot of the stuff I've shown you so far kind of provides some groundwork to do this kind of reasoning. In particular, I can look at this image, I can infer from this two-dimensional image the three-dimensional structure of the world. I can also infer, possible histories that the car was driving, and clearly crashed. But I can also ask questions which are outside the realm of normal probabilistic inference. In particular, I'm saying that they're lucky because had this barrier not been here, they would have tumbled down this hill. And so this is fundamentally a causal question and not a probabilistic question. Another example is from a few months ago now, when Vice President Pence said the following. He said, if the swine flu had been as lethal as the coronavirus in 2009, when Joe Biden was vice president, we would have lost 2 million American lives. So this is it's a counterfactual statement, indicative, or indicated by the would have. And I bring up this example and the previous example for a few different reasons. One, they require models of the world. This statement is built on a model of the world. Two, they're important. Causal and counterfactual statements are everywhere in our everyday lives. And three, there's a sense in which counterfactual statements can be true or can be false, or at least can be likely true or likely false. So in this sense, most people would say that there's a sense in which this is not true because had swine flu been as lethal as the coronavirus, most people would imagine that the Obama-Biden administration would have acted differently to if it was swine flu. And so we want machines to be able to reason correctly and coherently about counterfactuals using these complex models about epidemiology or inverse graphics or inverse physics and so on. And so this is kind of the motivation for this next project. And so what is a counterfactual? Okay, so at a high level, a counterfactual combines conditioning with interventions in a particular pattern. So what I'm showing you here is a conceptual model. So I have my time axis and I have some abstract state space, and I'm just showing you different samples from the model. So on the left, we have these unconditional samples, and in the middle, I've added some data points, these red points. And so when I add data, I condition the model just like we've already described. And so now all of my trajectories have to go through my data points. Everything's fine, conventional up until this point. But now I'm going to ask a counterfactual, which is to say, how would the world have been different under some intervention, which is what I'm showing you with this dashed line in the middle. And so an intervention in some sense breaks the world. It cuts the causal chains. And the curious or strange thing about a counterfactual is that I've invalidated my data, right? So my trajectories are no longer going through this red point on the right-hand side. But at the same time, all my trajectories are somewhat influenced by my data, right? And so we have this weird duality between being invalidated by the data and also simultaneously being influenced by the data. So I'm going to extend our Alice example just to give a very concrete counterfactual. So suppose again that Alice has a coin, it has some weight. Alice flips the coin, but now Alice has got a friend called Bob, and Bob is going to guess the outcome of Alice's coin. And if Bob guesses correctly, Alice gets $1. Otherwise, he gets nothing. And so suppose we observe that Bob guessed heads and won. The counterfactual query is, would he have won had he guessed tails? And intuitively, the answer is no, right? Because Bob guessed head and won, and therefore Alice's coin was heads. And had he bet tails, he would have lost, right? And so we want systems that can do this kind of reasoning automatically, right? And so this is a classic example from Judea-Pell, extended a little bit. And if we look into the counterfactual statement, it's given what we have observed, would Bob had won had he guessed tails? And this, the formal expression for that decomposes in the same way. So we observe O, we condition on that, and we want to know, would Bob have won had he guessed tails? And so the unusual thing here for some people would be this do thing. And this is an intervention. It's this cut I showed you into the causal history of the world. And we notate it with do. And so to do this mechanically, we start off very similarly to before. I'm not going to go through all the details, but we have our model, we add data, we restrict our model, everything updates as we've already described. And the main thing about a counterfactual is after we've done all that, we now make a copy of our world, which is changed in some way, which is our hypothetical scenario, right? And so in this case, Bob has changed to be forced to be tails, Bob's guess. And our system is predicting that, yes, in fact, or no, in fact, in this counterfactual world, Bob would not have won, right? So again, the details are, we can go into it later, but the high level point is that we do two things. One, we condition the world, or first we describe the world, then we condition the world. And then in this conditioned world, we make a kind of a structural change, and that structural change is influenced by our original world. And this is our counterfactual. So counterfactual models have been kind of formalized in the context of causal graphical models. And a lot of our work has been extending those ideas into programming languages. And there's a lot of kind of both reasons why we want to do this and also kind of technical difficulties, which are in the paper. I'm not going to get into so much. I'll just show you with some examples. So in this case, we have a kind of a dynamic population model. So we have preys, let's say rabbits, and we have predators, let's say wolves. And they are interacting in this kind of a dynamical system. And so suppose we go to some scenario and we observe that there are too many rabbits, there's too many prey running around. And so what we want to know is, as some kind of conservationists, had we made some intervention in the past, could we have avoided this situation? This is a counterfactual statement. So in particular, we can say, had we culled the prey in the past, could we have avoided this situation? Had we increased the predators in the past, could we have, how would things be different? So what I'm showing you here are just some particular trajectories, but fundamentally this is a probabilistic statement, and so we can only really ask about kind of expectations and histograms about the possible treatment effects. And so the very cool thing about this is that we are combining what is a fairly sophisticated dynamical simulation model, and we are embedding causal reasoning into that model. And we can do something a little bit more advanced. We can say, rather than just intervene at some arbitrary point in history, some arbitrary point in the past, a more natural thing to say is, had we culled the prey at their peak, at the optimal time? And so what we can actually do in the system is say that the intervention point, or the properties of the intervention, can be a function of the data itself, and that data is determined by the posterior distribution. And so by using a kind of a programming language, we can actually ask fundamentally different kinds of questions than you can do in the kind of the classical causal model paradigm. Another example is using a kind of inverse planning model. So we can say that we have, what I'm showing you here is this kind of a toy grid world, and we have a population of people who live in this grid world, and each person has kind of a belief about the world and also a desire about where they want to live in the world. And so what I'm showing you in the kind of the black and white images are migration patterns from different points in the world, how many people move from point 2 to point 3 and so on. And so we can do inverse planning or inverse reinforcement learning. And so we can observe some migration patterns and we can figure out the beliefs or the desires of the populations of our grid world. But now we can go beyond that and we can ask a counterfactual, which is to say, how would people have migrated had there been this barrier, this gray barrier between these different islands? And so again, we're combining a fairly sophisticated MDP style model with the ability to construct interventions into that model. We can also ask questions of causation. Does A cause B? And so in this case, I'm asking, does throwing the projectile at this angle cause it to hit the ball? And our system is basically answering yes to this query. And the way that it's doing it is it's making interventions into the angle of theta in order to find a scenario which invalidates the ball being hit by the projectile. And this is in some sense very common sense, and seems almost trivial. But the goal is to build systems which we can simply pose these questions to, and it can compute the answer. A slightly more advanced causal question or actual causation question is as follows. Is the gray ball on so focusing on the left image, is the leftmost gray ball the cause of our inability to see the yellow ball? So again, we pose this question to our system, and it starts making interventions into the world to infer that, yes, indeed, the position of the gray ball is the cause of our inability to see the yellow ball. What's interesting about this example is actually we're doing all of the stuff we talked about in the start of the talk, inverse graphics, because we don't actually, the system is actually observing these two-dimensional images, inferring where it thinks the balls are in the world, and then on top of that, doing this causal query. And so the goal of a kind of a compositional system is to be able to combine all these different parts and for it to be able to reason coherently. So this is the end of this kind of section on causal generative models. But the high level picture that I want to convey is that by embedding causal reasoning into kind of probabilistic programming languages, a whole host of new kinds of inference possibilities open up. And again, there are many different technical issues which arise, which I'm not going into, in particular when you get to things like loops and invariances, and what does it mean if I change this variable and new variables are created. But the high level mission is to be able to build a system that can really ask and answer causal questions about very sophisticated probabilistic generative models. So the next section, I'm going to, just taking the time, next section is of a slightly different flavor, and it's about learning algebraic structures. And a lot of the stuff I've spoken about so far is pretty high level, kind of symbolic AI embedded with probabilistic reasoning. And this project is kind of driven by the question of how can we kind of build learning-based systems which can start to incorporate some of the high level knowledge, which seems to be kind of fundamentally useful. There's this kind of bridge, which I'm sure many of you aware of, have talked about. How do we build AI systems which kind of bridge this neuro-symbolic divide? And this is one kind of answer to part of this question. So one of the most fundamental things you see in a programming language are data structures, things like stacks, dictionaries, tensors, numbers, and so on. And these are structures in the sense that they, well, in the sense that I'll describe in a moment. So a structure really has a few different parts. One is some set of values, and then the other part is some operators which kind of modify the structure. And finally, there are laws which describe how these operators should behave. And so what it means in some sense to be a number is defined by the operations that are defined in a number and the laws in which those operations should adhere to. A canonical structure is a stack, which again, I'm sure everyone is familiar with. And so for a stack, you have something like a push and a pop and sometimes more operators. And just to give an intuition about what I mean by laws, the law of a stack is that if I push some item onto a stack and then I pop from the stack, I should get back the same item and I should get back the stack returned to its initial state. And so the intuition behind this project is to say that actually, well, there's this idea from Ma, which I'm sure some of you are familiar with, which is that you can describe a system at many different levels. The computational level, what is the system doing? An algorithmic level, like how does it actually do it? And then the implementation, what is the code or the hardware or even the wetware if it's a physical brain. And we should be able to take this idea of a stack and actually implement a stack or any data structure really under a completely different internal architecture. And so what I have here is what we call a neural stack. And what it means to be a neural stack is the same thing as any stack. We have these laws that we have to adhere to, and we have these operators. The main thing now is that these operators push and pop are now going to be neural networks, and they're going to operate on this internal, somewhat opaque representation of a stack, which is just going to be some n-dimensional vector. So how are we going to train this? How are we going to embed our laws into this kind of neural stack? And so the way that we approach this problem is an idea called observational equivalence. And what I mean by that is that we write a program, and this program just uses the stack. So just think of any kind of arbitrary program. And we're going to run this program with our normal stack. And we're also going to run this program with our neural stack. And we're going to check at points in this program whether our neural stack and our kind of our conventional, Python or Julia stack are equivalent. right? And equivalence is defined in terms of some kind of measure of correctness or some loss. And so what it means to be correct, what it means to adhere to these laws, at least with respect to our program, is that these two executions of this program with these two different kinds of stack essentially produce the same thing. And you can formalize this in various different ways, but that's the high level idea. And so if you do this, you have these neural networks, you have these constants, you run these programs, and you try to adjust the parameters of your neural network such that you minimize this loss, which is kind of taken at these different points in the execution of this program. And so what we can do after training is, build a stack. This is the goal, and this is how it's achieved. And so what I'm showing you here are on the top row are digits just from MNIST. And on the middle row is this internal representation of the stack. And so the first thing, this empty stack is a constant, which is learned simultaneously with the functions push and pop. And the first key point is that our stack works in the sense that if we push on 8 and we push on 6 and we push on 4, and then if we pop, we get back, pop 3 times, we get back 4, 6, and 8 in order. And so this is showing you that our stack is working as the stack should work, as in we push on some items, some digits, and we pop and we get back the correct digits. The more interesting thing is that if you look at the internal representation, how does it do it? So it has a kind of a difficult challenge. It has to internally represent, multiple different objects and also have the relevant information to extract them in the correct order. And if you look closely, it's using some kind of strange interlacing strategy. I can't quite describe, I don't have a formal explanation of exactly what it's doing, but it's having to interlace all of these different items in a way such that it can extract them in the correct order. If you use a different structure like a queue, which is similar to a stack, but just has a different first in, last out order, or first in, first out, first in, last out, you get a different internal representation. Again, I can't give you a description of exactly how it's doing it, but it adheres to what it means to be a queue, and the stack adheres to what it means to be a stack. One thing we tested was the degree to which this generalizes.
Hey Zenna, there's a question,
Sure.
but unfortunately I'm somehow no longer host, so I cannot unmute the people. So I think you'll have to do that in the list of participants or someone else. Or you can make me host again and then I can do it.
Okay, I will make you a host. Okay, you're the host.
Okay, give me 10 seconds to figure out how to do the next thing. Okay, yes, now you're allowed to talk.
Oh, hi. I just had a quick question about this neural stack. So when you push into it, are the images that are pushed into the weights of the network, or does the network have access to an auxiliary structure?
No, they're not pushed into the weights of the network. So if I go back, so the input to push would be a pair. One is whatever the current stack is, and then the second part would be the item that you want to push onto the stack. So the weights of the network are fixed through training. Does that answer your question?
Then where does the image go when it's pushed? How does the network know to fetch it back?
How does the network know how to? So could you elaborate? I'm not sure what you mean.
So the network sees the image, right, when it's being pushed, like as a tuple with the push command. So the network takes the image and the push command. Where does the image go so that when the time comes to pop it, it fetches it back? So it doesn't go on the weights. Where does it go?
So okay, so there's this internal object which is the stack, right? And originally this is going to, so the way that I've encoded this at the start is literally a matrix, right? So here is the empty stack, and this empty stack is learned, right? So this is parameterized and it's learned during training. And so when I push on the item 8 onto this empty stack, so what this middle row is the stack, it's the internal representation of the stack. So the image goes there in some sense, like in some entangled way. And if I push
that image, is that image the top of the stack, or is that the whole stack in the middle row?
that's the whole stack. So if you look at the next image, it has both 6 and 8 inside the stack. And if you look at the next image, it has both 6 and 8 and 4 inside the stack. So the stack is this opaque thing which we can push to and pop from, and it works as a stack. But it's not a stack similar to what you would write in a conventional programming language. But it is in the sense of what it does. That's kind of the point.
Thank you.
There's another question in the chat by Stephen. How many items can be pushed? Is it possible to have stack overflow? There's a fixed memory size. Yeah.
Yes, so that's what I'll talk about in this next slide. So these networks are trained through some kind of behavioral equivalence, like I said, on some target programs. So by target program, I mean you write some program that uses the stack. And as you described, right, if the internal structure, if the internal representation of the stack is bounded, then you can't expect to put on an unbounded number of items. And so what I'm showing you here is that we train this network to be able to store, or we train the stack to be able to store basically 3 items. And we wanted to see what would happen if we tried to use it for 4 items. And so what we're doing is pushing on 8, 6, 4, 1, 6, 3, 4, 9, 1, and then popping, popping whatever 10 times, right? And as you can see, it reconstructs 1, 9, 3, fine, but once you get to 4, things start to kind of degrade, right? And so these are noisy stacks, and it turns out that actually you can stack quite a lot of things on, right? So you can actually stack a fair amount of data. This was trained to 3, but you could actually do a lot more. But there is this kind of fundamental limitation, which is that these are boundary representations, and you could view that from different sides. On the one hand, there's a plus to that. We are kind of exploiting the distribution to do more than we could with a conventional stack. On the flip side, you may say that this is not the kind of stack that you want to use in a normal program. But that's not really the motivation. So hopefully that answers the question. Feel free to follow up if it doesn't. And so some of you may be aware that there's work with using kind of stacks and so on in the neural network literature. The main distinction between this work and that work is that we have not hand designed an architecture for stacks. Actually, you can take any structure and encode that structure through the mechanism that I described. And so the point is less that we want to kind of hand tune new architectures for different data structures, and more that we should be able to build new kinds of neural networks and learn systems which can incorporate data structures, not through an architecture change, but by just encoding what it means to be that particular data structure. Okay, so I'm going to talk a little bit about open problems and where I'm going next. So there's a bunch of stuff that we've been working on over the last few years. This first project is on parametric inversion. And a high-level idea, in a nutshell, is that a lot of the stuff I've talked about so far, especially in terms of inference, is how do we essentially find values which are consistent with our data? Right? How do we find inputs, or how do we find values of latent variables? How do we find 3-dimensional scenes which are consistent with our 2-dimensional image? And the way that I've done that is through some kind of soft relaxation and so on. But fundamentally, it's an inverse operation. It's an inverse process. And so one of our biggest long-standing projects is about trying to run these programs backwards directly. And if there were more time, I would talk more about this, but the high-level idea is that you take your program, you define inverses for every primitive in your program, a little bit similar to the softening kind of program transformation, and then you invert the order of the execution. And it turns out that this is kind of a sound way to derive inverses of programs. This middle work is about, again, a kind of inference problem, but this is really about questions like, if I say, okay, the probability that it's going to rain tomorrow is 50%, what does this mean? How can I use this statement? It's not a normal kind of conditioning statement because I'm saying that some probability takes some value as opposed to some variable takes some value. And it turns out you need slightly different machinery to understand how to incorporate that kind of knowledge into your generative models. Finally, we've got some work on program synthesis. Like one of the benefits of using kind of universal probabilistic languages is that you can define the problem of inferring the model itself as a problem of inference. And so we have some published work in reinforcement learning, trying to infer kind of models for policy learning. And some of the new work we have is a kind of a new dynamical interactive environment where we're trying to have an agent interact with the world and infer the infer the causal model which led to that world through a kind of experimentation. So we're really trying to model the idea of a scientist interacting with some causal mechanism to infer the model of that mechanism. And finally, stuff I'm hoping to work on in the next few years. One is to really to take all of these ideas and to build a system that can answer why questions to explain things. So there's a lot of work in explainable AI, but I think there's a fundamental gap between what people are currently used when they say what they currently mean when they say explainable AI and what a human understands an explanation to be, right? So I want a system where I can say, why did this car crash? Why is there a car, this pileup? And it can say, well, the reason is this driver, didn't see this other driver, or this driver was drunk, at this high level declarative sense. And I think to do that, you need to combine program synthesis, you need to combine causality, and all of the ingredients that I've described so far. This middle thing I'm calling superstructure inference really comes from my observation that you can understand models at various different levels, right? So a light switch, at some level, you just press it, it comes on. At another level, I understand the internal circuitry. And how can we build systems that can reason about these models at these multiple levels of abstraction coherently? And finally, using all of these tools to try to do some social good in the world. And there's, this is an image of gerrymandering, which is something that we're thinking about. How can we deploy kind of the best in probabilistic machine learning to help the world in some substantial way? So these are the things that I'm thinking about and the stuff that I've done. I'd just like to thank my collaborators, my advisor, Amanda Sola-Lizama, and Josh, and my collaborators, James, Jean, Javier, Rajesh, and my Europe undergrad collaborators, Ria and Edgar. And with that, I will conclude.
All right, thank you. Very nice talk. So I think we have time for questions if people want to raise their hand. I'll unmute them. There's also already one in the chat. Why is the neural network stack noisy? Could you clarify that?
The neural network stack is noisy. So it's noisy here. The reason it's noisy in this case is that I'm asking it to do something it's never been trained to do. So this is a kind of a generalization error. So like the program which we trained the stack on pushed on 3 items and popped 3 items. But what I'm showing you here is the kind of an out of distribution example where I'm pushing on 10 items and I'm popping off 10 items. And so it's outside of its training distribution. But at some level, going to the previous question, this is a fundamental property, which is that this is a bounded data structure. The internal representation is this matrix of only so many bits, and so I can't expect to have a unbounded stack with a bounded internal structure. And so the neural network will fundamentally have to make trade-offs to handle this limitation. You could imagine, some internal representation which is unbounded in the way that a normal programming language is unbounded, but then you'd have to give up things like differentiability and so on, and training it would be a lot more difficult. And so, yeah, that's why it's noisy.
So on the similar question, I was wondering, so the stack is trained specifically on MNIST digits, right? It's not supposed to be able to stack anything else, okay?
Yeah, so you could imagine, making a parameterized stack, and I think that would involve modifying the weights in some strange way. Like you could imagine having some function which takes in some data and then determines the weight of the neural stack, right? Which would be a little bit like how parameterized functions work in programming languages.
Right. The optimization could become like adversarial, where you hypothesize the worst possible image to put on your stack and then try to course correct for that one. Or yeah, I can see how you can do more. Yeah. Cool. There was another person that raised their hand, so feel free to unmute.
Hey, so I had a question about the counterfactual statements. So is the point of that to like first condition on the data to create the models and then condition again to create like inferences? Was that the point of the interventions?
Sorry, could you say it one more time?
So just for like my clarifications, like the way that I understood was the point of the interventions was to like recondition the data, the model that we've created with the conditions to kind of create inferences. Like that was like the point, right? Like with the had X happened, can Y happen? We're like trying to recondition the model that we have with X to predict if Y can happen, right?
Yeah, well, I wouldn't call it conditioning, right? And so, so one example that people often use in the causal literature is suppose you have a thermometer, right? And so if you observe that the thermometer reads, I don't know, 100 degrees Fahrenheit, then you might infer many things. You might infer that the oven's on, or that there's a fire, right? Or that it's just extremely sunny outside. But if I were to go and intervene in this thermometer, take a screwdriver and like, force it to read 100 degrees Fahrenheit, I wouldn't conclude that there's the oven on or it's sunny outside, right? And so an intervention models this process of changing the system without and breaking the normal causal links, right? And so it turns out that this is a fundamental thing that you need to do. And so if we look at these counterfactual statements, like this one, right? So, okay, so what do we, there's in any counterfactual question, there's a kind of a hypothetical part and a conditioning part. And so the hypothetical part in this scenario is, had the swine flu been as lethal as the coronavirus, right? Which it wasn't, right? This is why it's the hypothetical, right? Yeah. The conditioning statement is implicit. It's not explicitly stated, but the conditioning, what he's really conditioning on is all the things that have happened over the last, a few months, right? And so there's this pattern of combining these two things where I'm conditioning on my data, which is what I always do, right, to get some information about what I should now believe. But then I construct a counterfactual, which is to change the world in some structurally different way, and that may be completely inconsistent with what I know already. Right, so interventions don't have to adhere to anything really. They are hypothetical, so you can just state things to be true. And so you should think of them less about adding information to your system, and more about constructing some hypothetical alternative reality, which could be different in arbitrary ways. And there's information shared between these two worlds because they both rely on some kind of shared latent structure.
Okay, and given this like intervention, like for this example, what would like a potential, the outcome would be like our model is consistent with this hypothetical, or it's inconsistent, right? That would be like the outcome. So like say a model was generated for like this example, right? With condition on coronavirus. Like so those would be the examples, the output, right?
So if you, so the output would be, so the output would be like you'd be able to compute whether this is true or not.
Right. If the model is consistent with the statement, pretty much.
Yeah,
right?
yeah,
okay,
yeah.
Got it. Thank you.
Any more questions? I see someone has their hand raised, but maybe they already.
Yeah,
I'll go.
I have just a sort of general question on the probabilistic programming languages. How does it play into some of the things that you've discussed in this presentation? For example, what do you provide? What do you declare in the language, and what kind of can I give it a graphical model in some form and structural equations, and then ask it a counterfactual query and have it and then combine that with the more traditional data structures and control features of a typical programming language?
Yeah, so yeah, so you know, maybe it's funny because I work a lot on programming languages, but I didn't show you much code, right? But in terms of practical tools, we have a probabilistic programming language called Omega, and Omega basically has these two operators, do and condition. And so you can take a program, let's say a physics model, a physical simulation, or let's say a graphics model, a rendering function like we talked about before, and I can condition it, or I can intervene on it in arbitrary ways. And so there's basically, you can pose any kind of combination of do and condition to construct a counterfactual, or even to construct different patterns which are not strictly counterfactuals, but use both conditioning and interventions in arbitrary ways. But the basic answer to your question is that we have these two operators, condition and do, and they allow you to take your program and automatically transform it either through an intervention or add information through conditioning. And so we can, all of these examples like this and so on is done by first writing a model, a dynamical, a system of dynamical, a dynamical system, and then conditioning the model with data using the condition operator, and then using the do operator, our version of the do operator, to go in and make these interventions.
And I would specify the model in something like Omega with A leads to B, and maybe a structural equation for how A depends on its variables.
So it's not like a DSL within Omega. You just write your program. So you don't have to do any kind of special. It's not like a structural equation model. Like we've extended the principle behind structural equation models to normal, full, complete programs with control flow. Like you would just write a simulation as you would normally write a simulation for these models. Does that make sense?
I think so. I'm gonna download Omega and play with it.
Cool.
I see still several hands raised. I'm not sure if they're still current. Otherwise, I guess. Oh no, I see a new question. Is there a way for your programs to update their constraints predicates placed on the world as new observations come in?
I'm not sure.
So I guess it refers to the MCMC algorithm, where maybe you have some new observations and you want to update your MCMC chain.
Yeah, so normally the constraints don't change as a function of the data. It's like you have your constraints, you have your thing that you want to condition on, and then you do a transformation to make that conditioning more tractable. And that can work with various amounts of data. But I wouldn't say that the way that these constraints, I wouldn't say that the relaxation depends upon the data itself, except for in some kind of gnarly technical way, which again we can talk about in more detail. But at a high level, you can add more data, but your constraints don't vary as a function of your data necessarily.
Hi, I had a quick question about the, I think it was 2 slides ago, you were talking about daisy chaining a few, oh yeah, right here. Yeah, so in the next transition, a counterfactual subgraph emerges, right?
Mm-hmm.
So in that next slide, does the model learn that entire structure in pink on its own, or do you give that to it and it only learns the parameters?
So when you basically when you write this, when you write this expression, it constructs this thing. So the do is saying, I want B to be forced to be true. And so it's constructed a copy of your model such that B is true and everything else is maintained, right? So you don't manually do this. This is in some sense automatic, and it's a kind of a result of your counterfactual query.
I see. So the models have access to the entire realities of the world except the very causal query we want to answer. Like when you formulate the problem, right? There are like many variables involved.
Yeah. So
it has access to these, but not the causal connection for whatever two variables you want to test.
Yeah. So it's like you start with your base model, which is this, right? This is the model of the model up to the last line. Theta A, B, win, and so on. And then whenever I construct a counterfactual query, in this case, I've set B to be true, conditioned on something, that's going to essentially construct a new model, which is going to be different in some way, right? So there's a kind of a fundamental point here, which is that if you know the exact query that you're trying to ask, right? Like, for example, this one, then you could just manually construct this counterfactual model yourself, right, as the modeler, right? So, and that's fine. One of the points of having a system or a language for counterfactual reasoning, and to be able to do it in arbitrary programs, is that I shouldn't tie the question that I want to ask to the model itself. I should just be able to ask the question, and the system should be able to construct the appropriate mutations or modifications to my model to be able to ask that question, right? And this is going back to this original motivation, right, for common sense reasoning, right? Imagine if I had to build a new model for every, question that I had to ask, right? That seems like it's the wrong approach. I should just be able to have my model and be able to ask questions about my model, and for it to automatically produce the kind of the correct transformations to that model to be able to answer the query.
I see. I was just wondering, so when you formulate this question this way, what if the causal connection is not direct? Say there's a hidden variable, or let's say a second variable must be present for the causal connection to activate. How do you handle these?
So this, I think there's different questions. So this is, this is model-based inference, right? So you write down your model and you can ask counterfactual questions relative to that model, right? If there are things in the real world which are not in your model, now you have an issue, right? You have a problem. Well, you may have a problem, right? And so there's another question which is fundamental to causal reasoning and causal inference in general, which is that given some observational data or even some experimental data, how can I infer the model of the world? This is sometimes called causal discovery. It's heavily related to kind of program synthesis. And also another question is, if I have a model and I know there may be some factors that I haven't accounted for, what kinds of queries can I make? It's kind of your question, right? Maybe there's some hidden thing which is affecting this thing, but I don't know what it is, or I don't even know that it exists, right? And so there's a whole world of things, and they call it, identifiability, and this is kind of these are key questions in the causal reasoning literature, and they all the approaches and all the problems still apply in our case. The main kind of differentiator in our case is that we are now in a much more expressive language than structural equation models, right? We're in the language of fully universal programs, Julia, Python, or whatever, where you can pretty much do everything. So everything becomes a little bit harder, but the conceptual problems about identifiability remain, regardless of the particular representation.
I see. So those are handled separately.
Those are handled separately, yeah. And there's no magic bullet to these issues.
Thank you.
Okay, so thanks everyone for joining. Thanks, Zenna, again for a great seminar. And yeah, I think we can wrap it up. Okay.
Cool. Thanks.
Bye-bye.